usually love to be rolling around, but I think it's okay to stay here. Yeah.
And again, like you have made a giant effort to come here. Always make people very appreciative. So whenever you want to come.
Okay, thank you.
Okay, welcome everyone. Welcome to the Physics Club. Welcome to being here in person. This is our second in-person Physics Club of the year, so yes. And attendance, the attendance, there's confusion here and there, so we appreciate your patience in getting started just a little bit later than usual. It's a pleasure to welcome Jun Ye, Physics Club speaker for today. Jun received his PhD from the University of Colorado at Boulder. He did a postdoc as a Millikan Fellow at Caltech, and then returned to the faculty of the University of Colorado at Boulder and as a member of JILA. In his time, he's received a large number of awards. I'll give you a very abbreviated list here. Early in his career, he received the Optical Society of America's Adolph Loeb Medal. He received the prestigious Department of Defense P-Case Fellowship. He received the American Physical Society's I.I. Rabi Award and the American Physical Society's Norman Ramsey Award. He was inducted as a member of the National Academy and received the IEEE I.I. Rabi Award. More recently, he's received the Micius Quantum Prize from the Chinese Academy of Science, the Breakthrough Prize in Fundamental Physics, the Niels Bohr Institute Medal of Honor, and most recently the Herbert Walter Award of the German Physical Society. So this is a measure of Jun's impact as a scientist, but what I wanted to mention briefly was the breadth of his work. So in the field of atomic and molecular and optical physics, Jun is one of the very few people to make a substantial contributions to all three of those efforts, in atomic physics, molecular physics, and optical physics. He's also a rare individual to make important contributions to what I would see as the three scientific pillars of this field: precision measurements of fundamental physics, quantum many-body physics, and quantum information physics. All of these are represented amply in Jun's body of work, and it's a truly impressive record. So we're looking forward very much to today's talk. Thank you, Jun.
Thank you very much, Jack, and thank you everyone that have had a wonderful time touring Yale. Just find it very excited by the visions you guys have for the coming decade, quantum science and many areas of physics. So thank you for inviting me. I feel honored to be only the first, non-local speakers for the in-person colloquium. And I hope in the next 45 minutes, 50 minutes to give you some entertainment on the modern sort of atomic clock building process, that we have a lot of efforts here on campus, taking quantum science, putting engineering to it, build a quantum machine that's actually functioning, that can actually process information. And I'll tell you a bit of a different flavor of quantum science, using this to measure things better. So what I really want to tell you about is actually some very recent work. Let me see, should it work? That we were able to measure gravitational redshift that was predicted by, of course, by Einstein's relativity long time ago, and that has been tested. People fly clocks in the satellites, in airplanes. But what's really exciting, and I'm not claiming we are testing general relativity any better, but we can see it at a minuscule length scale at a few hundred microns. And you can imagine if we put a quantum entanglement, science, all these things together, maybe in the next coming decade, we will be able to see gravitational redshift, the curvature of the Earth on your time effect, dilation effect, at a micron scale, quantum mechanical wavelength, where you can have entangled atoms along the vertical plane or along the horizontal plane. They will have a different dynamics because of the curvature. So I thought this could be an entertaining story to tell you how we get there. And of course, the clock after World War II, we heard those names of Ramsey, Rabi, and these are pioneers that you really look up to learn from them. And in fact, they have made a tremendous progress. That they means the body of the work of the entire scientific community following the blue line. You can see the performance of the clock improved every decade of the human society. And that's kind of amazing. And it's getting all the way down to 10⁻16. at that level, you start to hit wall because those atomic clocks of early generations are based on microwave transitions. There's a 9 gigahertz transitions. And you're talking about 10 to minus 16, meaning you would have to have 10 to the 6 seconds or so to be able to see you're missing a cycle. And so from that point, people say, well, why don't we go to a much higher frequency? So that number of cycles per second is much higher, like optical domain, where the number of cycles per second can be higher than microwave by 6 orders of magnitude. In the early 90s, when people start to think about this, well, the coherence time of these optical clocks are still much, much worse than the microwave clocks. But as the technology moved forward, you can see the progress over the last 2 decades being amazingly fast. And this progress is still continuing. The reason why I'm very positive about it, if you think about the list of quantum technology that's coming out to enable these optical technology, optical clock, whether you're developing very high quality factor optical transitions, there's the cold atom physics, new laser stabilization tools, putting atoms in optical lattice to study engineer many-body quantum states, the invention of optical frequency comb to connect optical frequencies with microwave frequency. All these things that I'm talking about are very recent, 2 or 3 decades. And many of them are very much science. We have seen
ride of her little life. And look,
Can I just invite everybody who's joining us by Zoom to mute their microphone?
Thank you. And if you have questions, I will be more than happy to entertain questions in the middle. Just let Jack know. So what I'm saying is, this is a kind of a conference, just like a quantum information science right now. 15 years ago, we were hearing from Rob about, Schrodinger cats in superconducting circuits, and now we are processing information. So this is how fast where science, engineering are coming together. It's the same story with the optical atomic clock. Current accuracy of those clocks have reached the 10 to minus 18, meaning if I build this clock at Yale or I build a clock in Boulder, Colorado, as long as I understood all the systematic factors, taking them into account, these clocks agree at this level. 10 to minus 18 meaning, you move the clock by a centimeter, the gravitational rate of shift is at that scale. Precision, however, is a lot better. It's at 3 parts 10 to the 19. And this was actually done back in 2019, just before the pandemic. And I made that chart at that time. I said, well, we probably will get to 10 to minus 20 in the next 5 years or 10 years or so, just because if I have strontium atoms like this with a long coherence time, very high quality factor, I should be able to predict, just because I don't see any fundamental roadblocks to make better things. Over the pandemic, things worked out better in the laboratory. And in fact, we were able to shoot past the 10 to minus 20 yardstick and now can claim clock measurement precision at the parts 10 to minus 21 level. That does not mean that I guarantee the accuracy yet. That requires you to check all the systematics, but at least I know I can use this to measure gravitational rate of shift. And that number, 6 times 10 minus 21, meaning if you change the gravitational potential of your clock by 100 micron, 200 micron, you will be able to see it. And this is exactly what we saw. Yes?
What's the difference between accuracy and precision?
Precision just means that at the end of the day, I can measure something really well. The noise can be averaged away. I can tell you, my clock is every day I can average it down to 1 second per day, for example. That's a terrible clock, but that's a precision. But I did not tell you if this clock I made in Boulder, Colorado would also tell you the same time in New Haven. And the accuracy would have been no matter where you made it. In principle, any point in the universe, you should be able to bring those clocks together and make a comparison. And that included all the gravitational shift effects. And in fact, the future of the clock making could be limited by the gravitational waves, because that's exactly what's going to limit us by the universe. And I want to make a comment about why the quantum science has played such an important role for making quantum sensors. And I know many people in the audience here are actually also not only just quantum information scientists, but also quantum sensor people. If you think about developing quantum sensors, there are certain ingredients you want to design a system with very long coherence time, and this is your quantum system design. You want to put lots of atoms in there, or whatever the quantum particles you use, superconducting circuits could be. And those would allow you to build a many-body quantum state. But you want to make sure that on one hand, you can have lots of atoms to help you to gain the signal strength. On the other hand, you want to make sure that interactions of these atoms are not going to be in the way to limit the uncertainty, limit accuracy that you can claim that your device is measuring. In the future, we will have being able to actually have so many atoms that we can start to also incorporate entanglement and spin squeezing in this particular context to beat this so-called standard quantum limit, where the number of measurements gives you the precision limit, but we want to go beyond that. And so you can see the precision frontier comes from state preparation, comes from quantum coherence, and comes from optimal measurement. That defines the new frontiers of a precision measurement. And I really do feel this is a very exciting new frontier where you can have meaningful discoveries for fundamental symmetry in fundamental physics. On the other hand, of course, we have heard of this big revolution going on in quantum information science, entanglement resources, system engineering, and important applications that we build our quantum machine. What are we going to do with it? Those are important application questions to ask yourself. These are coming together, I think, defining a very exciting new quantum science. I would say physical science in general. This is what Steve Gervin says, quantum science broadly defined. This is actually really, I feel very much at home when you say that. So just step back a bit, what is actually clock in the sort of undergraduate level? This is what when Bohr initially in 1913, right? He wrote the first paper about Bohr orbitals. A lot of those concepts are not necessarily correct with the modern quantum physics understandings. But one key thing that is really correct and has been stated on is those stationary orbits, the quantum mechanical states. And he, at the time, of course, was using different classical language to describe it. And I call this Bohr's certainty that out of the nucleus, electron has different orbits, and the energy scale, energy separation between these orbits are defined by nature. And this is what I call Bohr's certainty. This is as good as it gets a natural unit of time, because the energy is actually fixed by the atomic structure that was born by the universe. On the other hand, in the quantum measurement, we know there's uncertainty. There's a quantum uncertainty, which comes from if I have a coherent superposition from ground to the excited state. That's when I make a clock, I want to put atoms in coherent superposition of two quantum states. This coherent superposition is no longer an eigenstate of the Hamiltonian. It's evolving. And when you finally make a state measurement, the evolution has this fundamental uncertainty. You don't know whether it's pointing down or pointing up. And that is the fundamental quantum uncertainty. So for clock, basically what we are looking at is shining a phase coherent laser at a coherent superposition of atoms in this equatorial plane, where the pointing down represents the zero ground state, pointing up is the excited state to 1 qubit. And it's rotating with the energy separation of their E. And you want to maximize energy separation E. That's why we were shooting for optical atomic clock. And you want to maximize the time T, which is the coherence time. And in the end, you're measuring how many cycles of this evolution that has gone by. That we can use this to define the time. So from here, you can see that the more atoms are involved in this measurement, the better the noise floor, the better the precision. The precision is defined as 1/√n, when these quantum pendulums are independent from each other. But if in the future, or future is actually now, that we start to use quantum entanglement into systems like this, you can potentially achieve measurement precision better than 1/√n, but rather limited by 1/n. So you have 1 unit of quantum noise with n particles playing together. To just tell you a bit about timescales, if we just talked about Bohr pendulum, if you think about how electrons are moving around the nucleus, the time scale is on the order of femtosecond, 1 part in 10 to the 15th second, fairly fast pendulum. And if you have this pendulum oscillating for 120 seconds, and I'm using this as example because it happens to be this 2 states from ground single S0 to triple P0 metastable strontium atom. The lifetime is 120 seconds. That the maximum quantum coherence we can have with this superposition here. You can immediately count that you have a 10 to the 17 cycles. If you don't do anything, just being able to count 10 to the 17 cycles, you have a measurement precision of 1 part 10 to the 17. And that's why it's so useful to have long coherence time and have a fast oscillation. On the other hand, the universe lifetime, if you expressed in seconds, 10 to the 18 seconds. And the geometrical mean between, on one side, a very microscopic time scale, on the other side, the very macroscopic time scale, that happens to be like a couple minutes. So it's kind of interesting if you think about strontium atoms, right, have us at this midpoint. And if you build clocks like this, really could have, on one hand, have a very, very microscopic quantum phenomena using this as your tool to measure macroscopic, sort of a cosmology kind of physics, maybe search for dark matter and so on. So in order to catch up with this quantum coherence, we obviously have to build this laser that I just showed in a couple slides ago. And this is a particular technology that we have been developing in collaboration with PTB, that's a standards lab in Germany. They actually have the purest crystals of silicon. And at the time, I was very fortunate. I was awarded a Humboldt something. I went to Germany and stayed in PTB for a couple of months, and we designed these cavities together. And the silicon has this interesting property that if you cool down to 124 Kelvin, the thermal expansion coefficient goes to 0. So you imagine you cool this thing down to 124 Kelvin. Actually, there are other points you can cool down to 17 Kelvin and so on. There's no more thermal expansion. That's a very stiff material. You drill a hole, you put a pair of mirrors up and down. That forms a very precise fabric pearl cavity with a finesse of, say, half a million. So the photon you put in gets bounced back and forth between these two mirrors for 500,000 times. And so you can build a very, very pristine, sharp interference for optical fringes. And you can use this to stabilize lasers. If you remove all the fundamental noise, the technical noise, excuse me, the fundamental noise turns out to be the thermal noise of these coatings. It's the same noise that's limiting the LIGO measurement precision. Essentially, like any material you have, once you have a mechanical loss, you will also have fluctuation, the dissipation fluctuation theory. And so as long as your temperature is not absolute 0, you always have fluctuation. That's what's limiting us for now. But we can test it by building 2 independent lasers. And just as we learn how music folks work, we bring them together and hear the tone, the beat. You can do the same thing with 2 lasers. And here's a tone that we hear from the 2 optical lasers, independent lasers beating against each other with the line width on the order of the millihertz or so. And this indicates stability at the parts 10 to the 17 level. And with the recent technologies of a so-called optical frequency cone developed by Ted Hinch and Jian Hao, we can now transfer this super really good stability of optical reference from one single color to the rest of the entire visible spectrum, to mid-IR, to X-ray. In fact, a comb like this, recently we did an experiment. I was talking to some graduate students. They were asking me questions about how does the research go? And I tell them, sometimes goes in whatever you dreamed about last night. And I was telling them, like, I can use these frequency combs now to measure people's breath and measure the molecules at the parts per trillion level, such that I can actually tell you with 90% accuracy, limited by PCR test, whether you're COVID positive or negative, just by breathing in. And this is just completely unrelated experiments to the clocks, but as a student, the sky is the limit. As long as you can imagine things, you can do things that can be totally useful. And with to translate this kind of coherence to the coherence time to coherence length, just remember that the round trip time between Earth and the Moon is about 2 seconds, 10 to the 15 waves. So if you don't have atmosphere, you can actually build an macrosync interferometer with one arm on Earth, one arm on the Moon, and you will be able to have the light bouncing back and forth between Earth and the Moon 60 times, and you can still see peak and troughs of your optical interference. And hopefully soon we'll be able to push this coherence length all the way to the distance of the Sun and Earth, because then that feel really good to say the laser coherence length spans one astronomical unit. So just imagine lasers like this with satellites flying around the Earth. You will be able to actually shoot laser beams from one satellite to another over hundreds of kilometers, because it's a phase coherent. You can actually measure the optical fringes, so you can actually measure the distance between satellites down to a small fraction of the optical wavelengths, therefore control the satellite orbits. Actually, if you think big, you can imagine lasers like this can allow you to connect satellites in an optical interferometry stable way, so you can take a gigantic image from distant galaxies and process information by bringing information together from 2 different satellites. So getting good enough lasers, of course, then we have to deal with atom. The traditional spectroscopy, you do that in the cell when atoms are moving around. But of course, we know from relativity, there are time dilation effects by Einstein's, whether you want to think about the velocity time dilation, motional time dilation, or gravitational time dilation. Each atom, if they don't have a controlled motion or velocity or position, they will not be able to tell you the correct time. And this is really the starting point of laser cooling. I always was told by, whether it's Steve Chu or Bill Phillips or Claude Continuity, when they started the laser cooling, was actually one of the key goals with precision metrology was exactly to solve this problem, Doppler problem. So with the laser cooling problem solved, we can cool these atoms down to like microkelvin, even nanokelvin temperatures. We still have to trap them. One of the pioneers, Ashkin, just passed away, but he was the one who came up with the ideas of optical tweezers, where the atoms can be trapped at the middle of the laser focus. But of course, the very fact that you can trap atoms is because you're creating spatially dependent AC stock shift of atomic structure. Therefore, the ground state atom gets trapped in the middle, but the excited state could be actually repelled from the trap. And if you are using the optical trap, here is a blue trap, and you try to do spectroscopy, even though the ground state atom is trapped. But as soon as you try to excite it, the atom may be repelled away, or at least your measurement precision or accuracy will be limited due to the fact that it depends on the light, the intensity of the light you're using. So we came up with this idea of so-called magic wavelength trapping, using the fact that atoms are not a 2-level system, but a multi-level systems. We can find the wavelengths such that AC stock shift of the ground state and excited state are exactly the same. And if that's the same, you can do spectroscopy within these optical traps. And whether you're in the ground state or excited state, the trapping potential looks just the same. Therefore, you're not compromised in your measurement precision. And if that's the good idea, then it should be very simple to implement in the experiment. You shine laser beam reflected by a mirror, and you have a standing wave. At the anti-node of the standing wave, that's where it's like a tweezer the atom gets attracted to. And this can be visualized as a stack of pancakes. At each trapping site, you can have dozens of atoms in there. And you can have hundreds or thousands of these traps. So suddenly you're talking about 100,000 atoms trapped in this, and you can start to do spectroscopy by sending the laser beam perpendicular to the direction, or co-propagate with the direction of this one-dimensional optical lattice. And it's actually a very dramatic sort of effect to show the quantization of the Doppler effect. The atoms, of course, optical transition, the wavelength is so short. So it's just a tiny motion, centimeter per second, kind of a slow motion, still gives rise to a very significant Doppler broadening. Here's a picture of when atom is at 1 microkelvin. And you can see the transition line width is broadened to something like 40 kilohertz, even when the temperature is considered very, very low, 1 microkelvin. And as soon as you put atoms into a periodical potential, the Doppler profile gets modified. And if you just make the trapping potential a little deeper, suddenly you see a very interesting phenomena where the center line from condensed matter physics is nothing surprising. The center line you would call zero phonon line, where they have no motional effects associated with it. And then you will see the motional effects are manifested in the 2 sidebands. The separation of the frequency of the sideband is exactly equal to the trapping frequency in these potentials. And you can see asymmetry between those sidebands. This asymmetry gets even more pronounced as you go to deeper and cool the atoms better. And the asymmetry comes from the fact that along this particular trapping direction, this one-dimensional propagation direction, you cool the atoms to quantum mechanical ground state. Therefore, when you drive it, you can only have either carrier or you gain one unit of a quanta, motional quanta, but you do not have below 0 motional ground state. There's no other states there. So therefore, the red sideband is suppressed. So this technique allows you to start to do spectroscopy where you can remove Doppler shift. There's no photon recoil because that's being taken up by the entire lattice. And the trapping frequency shift due to the AC stock shift is gone. And the measurement precision gets improved by square root of n. So that's all good news. It's until you start to looking into in greater detail. And in fact, this is how we get started. In 2005, we published the first paper saying this is the getting going. This is the first optical frequency measurement of strontium atoms. There was another measurement from Tokyo, University of Tokyo, Katori's lab, and we start to really move forward. And except when you start to look into what's the next budget item on your uncertainty. And if you expand in the middle pancake, you get dozens of atoms up there. When you do clock drive, you're driving every atom on the Bloch sphere from ground state to the coherent superposition of the ground and excited state. This little blob is supposed to represent the quantum noise that I mentioned earlier. And these atoms are actually fermions. And that's because we do not want atoms, if it's a boson, they're going to come together and interact very strongly. So we want fermions, at least they will avoid each other. In the transverse dimension, transverse meaning the transverse in this plane, they are still motional states. This is not a quantum degenerate gas at the time. These are actually thermal gas. So you have still motional states occupied, even though in the perpendicular direction to the pancake, it's in the ground state of the motional degrees of freedom. So for fermions, you have to anti-symmetrize the wave function for 2 particles. For example, you have this negative sign, n and n1, n2 representing the transverse motional degrees of freedom of 2 particles. And therefore, you can think of these two atoms are interacting through P wave. And S wave is when the motional states are symmetrized. So you have those populations, because those P wave interactions are rather weak, and they're nearly independent of the motional degrees of freedom in the 2D. Therefore, the population is actually frozen in those motional states, but the P wave can interact because they're interacting independent of n. You can actually think of all these atoms are moving around in those motional degrees of freedom, but they can have contact interaction when they come close enough. And all these atoms are doing pairwise interactions, but because they are hardly dependent on the motional sort of indices, you can pull this out and have a collective interaction suddenly as a long range in the momentum space. And so if you define a collective spin operator by summing together all these individual spins, you actually have a Hamiltonian coming out of this, where it's a collective spin-spin interaction. So it's the S dot S term. And it turns out you can have, depending on the microscopic collisional properties of atoms, you can write into a Hamiltonian like XZ squared. This is so-called single axis twisting, where depending on the population along the Bloch sphere, along the Z direction, you can have different evolutions along equatorial. So above, when SZ is above 0, gets pulled in the right-hand direction, while it's below 0, pulled to the left hand, you can see the quantum noise gets distorted. So we can measure all these. It's actually quite interesting. We were building atomic clocks, but in the end, we were actually starting to study magnetic model, Hamiltonian. So that was fun. But if you put your head back on saying, I want to build atomic clock, that's going to be a fundamental limitation, right? These interactions will make the clock inaccurate. And you have to find a way to using this kind of entanglement as a good resource, but you don't want to limit your clock accuracy. So at that time, we thought, well, let's redesign the system. We can either make a really tiny 3D cells, just like the Doppler effect, I can quantize it out. I can maybe quantize out these interaction effects by making the interaction really strong. The quantum mechanics oftentimes give us this anti-intuitive tools. Like if something is bothering you, well, make that something really big and they're out of the picture. Or you can actually engineer the interaction such that the interaction goes to zero. So I'm going to tell you a bit of both, just so that you get the flavor of what we were thinking in the lab back in not quite 10 years ago, maybe 7 years ago. So this is the approach we took for making a 3-dimensional optical lattice. Instead of having just a 1-dimensional interference, we now copy that in all 3 spatial dimensions. So you create this kind of a crystal. Because these atoms are cooled down to very low temperatures, by Pauli exclusion principle, one atom occupies one site. So that's perfectly good place where you will say interactions not turned off. But it's actually not really true. If you look deep down, when you start to drive every atom, you can immediately see there could be a dipole-dipole interaction. Now, this is actually the term we are now experimentally measuring at the moment. It's just at a smaller scale. Nevertheless, if you say I can scale the system up, 1 million seems to be a number people throw around anyways, a million qubits. So I said, okay, this was a few years ago. I said, I'm going to put 1 million atoms in there, 100 by 100 by 100. Coherence time is 120 seconds. I should be able to build a clock with a 1 second averaging time of a few + 10 to -20. That seems to be a really good goal to go for, because remember, LIGO measures the strain of when the gravitational wave comes. You see this quadruple field, and you're measuring 2 arms. The differential strain difference is 10 to -21. That same number will tell you about if you have 2 clocks, when the gravitational wave comes and the 2 clocks are spaced apart by gravitational wavelength. If you can measure time at 10 to -21, you will see gravitational waves. Just with clocks, you don't need it like this interferometer. So at that time, we were running clock at 10 to -16, 10 to -17. Okay, we got 3 or 4 orders of magnitude to go. But actually, just recently, we were able to push this now already to 3 times 10 to -18. So 2 more orders of magnitude to go. We'll start to become really interesting device, being able to actually go measure gravitational waves. But also, that kind of thinking also has given rise to another interesting set of physics, like people like Misha Lukin and younger researchers like Adam Kaufman, Manuel Andres, and I know that somebody who's close here, Jeff Thompson at Princeton, they have come up with new ways of doing atom trapping. Well, tweezer goes back to the roots. And in their case, the atom tweezer atoms can be individually addressed. It's not as densely packed in the optical lattice, so you don't have to use a quantum gas microscope. You can see individual atoms. And now you can think about what qubits. Now you can do entanglement. You can do actually operational gates with it. And indeed, people have demonstrated, Manuel Andres being the first and being able to show fairly high fidelity, not quite as competitive as trapped ion or superconducting circuits yet, but they can start to entangle these qubits. And with 10, 15, 20 atoms, you can actually do significant enhancement by using entanglement as your metrology. So this has given rise to a new set of sort of very, very good friendly library on quantum metrology platform. And this is what our field is so good about, kind of gave rise to new platform, new possibilities to do things. I just want to give a little advertisement to these late newcomers in the metrology side, because I find it very exciting. This is where metrology, quantum information processing, and so on all can be built in a single platform. So remember I promised that we're going to squeeze out all the interaction energy. So we get those atoms confining these lattice. And indeed, if you look at the side bands, it looks beautiful. You have a 3 set of blue side bands. That's because now you're confined, quantizing all 3 directions. And there's nothing in red because atoms are in the cooled and trapped to the ground, motional ground state. If the strontium atom actually turns out have a nuclear spin of 9.5. So if you have a little magnetic field, you will have 10 nuclear spin states. If we do a little poor job of not spin polarized, selecting a single nuclear spin, you can have, in principle, spin impurities in your system. What happens to them? If you have spin impurities represented by those colors, of course, these would represent as distinguishable fermions, and so Pauli exclusion principle does not apply. They can occupy, the 2 atoms can occupy the same ground state. And in that case, it turns out, just as I was saying, if the interaction energy was too small, it's actually the biggest problem. And they are just underlying this little carrier transition where representing a single atom transition. But if the interaction is so strong, they actually quantize the way, then they do not pull the frequencies of your clock transition. And there are two side bands, as you can see. And these 2 side bands come from the fact that when you have a nuclear spin and you have a electronic degrees of freedom, ground state, excited state, you have 2 different ways to symmetrize, anti-symmetrize the 2 fermions. It could be triplet in the electronic state and then singlet in nuclear, or singlet, triplet in nuclear, or singlet in electronic degrees of freedom. Motional states are already quantized to 0, so there's nothing there. So you can see that only 2 side bands. You may ask the question, well, you have 10 different colors of the spins. How come you only see 2 side bands? And turns out this is what's so-called a SUN symmetry, that these different colored spins interact with exact same strength electronically. So all of the different pairs of colors turns up into a single, in a single anti-symmetrized or in nuclear spin or symmetrized nuclear spin degrees of freedom. And we actually can see 2, 3 atoms, 4 atoms, 5 atoms stacked up, and you can always see 2 peaks, no matter, and those peaks of course are different. When you have 3 atoms, it's a different place, but you only see 2 peaks. We also put in a spatial imaging, very high resolution, because that's useful. And this is inspired by the quantum gas microscope work that happened at Harvard and among other places. We didn't quite get to the single site resolution. It's also hard to do this in 3D. But nevertheless, this was good enough. We can see 1 micron resolution, and you can apply a magnetic field gradient. And as you can see, this red-blue stripe happens to be, it's not American flag or anything, but it's actually the atomic coherence being frozen by the laser interacting with the atoms. And their frequency is shifted because you have a linear magnetic field gradient, and you can take an image of it. I advertise that you can find this magic wavelength. Experimentally, you have to search for it. And for example, here I purposely tuned 1 Hertz offset between the ground and excited state. And you take an image of it, it almost looks like a Newton ring. When you have slight different curvatures of optical surface, you take an optical image, you see those Newton rings. These are not optical images, these are atomic excitations by slight frequency shifts offset of the 2 Gaussian beams. So what we are working on is to build a so-called a band insulator, mod insulator clock. And I can tell you the reason why. If the trapping is too deep, it turns out, even though those magic wavelengths is very benign, nevertheless, the atoms still scatter off these photons, get lost at a time scale of 100 seconds or so. So we don't want that. We want a trap to be shallow, and so we want just those traps to be just holding the atoms, but don't scatter off photons. But when the trap is too shallow, they can tunnel. Atom can tunnel back and forth. When the tunnels, that happens to be the magic wavelength that gives rise to the lattice spacing. And the wavelengths we use to probe the clock transition, they are not necessarily commensurate. These are decided by nature. And so in that case, when the atom is tunneling back and forth, you can see it picks up a phase shift because it does not agree with the wavelengths of the laser they're probing the clock transition. That phase shift if you think about it, is your Doppler line width. So you can find a way to solve that problem, which is you can, instead of having the laser retro-reflected by mirror, you can have 2 laser beams coming with angle, and you can tune the accordion angle. And when you tune the accordion angle, you can tune the lattice constant. So this is a picture where the lattice constant is tuned exactly equal to the wavelengths of the clock. In that case, the atom can still, they can move around, but their Doppler motions digitized to a point where the Doppler motions always pick up 2 pi phase shift. Therefore, it does not matter. So ideas like this is something we are playing with in the 3D lattice. But now I'm going to end on the final story of making a big 2D. Now we have learned all these 3D. From the 3D, we learned all these interesting idea that we don't want the clock to be too deep, the lattice to be too deep. We want to take a good images to see microscopic distribution of the states, and we want to be able to engineer the lattice. So now let's put all this together, going back to the 2D system, the 1D lattice. If I do that, I'm just giving you to talk about that spin orbital idea one more time. Before we make the clock, the lattice is fairly deep, and you can think of these individual pancakes are separated from each other. They do not interact. When the laser comes, because they do not interact, it doesn't really matter. But now when you lower the trap depth, because we learned from 3D lattice that we do not want trap depths to be too high to limit us. These atoms can tunnel, and it's on top of which the laser wavelength is not commensurate with the lattice unless you do this accordion idea. So you can pick up these phases as you propagate between. But now, if the atom can tunnel back and forth, these atoms no longer identical fermions because they pick up different laser phase shift. And this is what we call the spin orbital coupled Fermi interactions. And this is something we can control. And now I'm going to use this technique of controlling the spin orbital coupling to zero out the interactions for the new clock that we designed. Is that a question? No. And actually, just to remind you that I showed you this Hamiltonian that I said we can do spin squeezing, but now with the spin orbital coupling, you can think of it as a fictitious magnetic field, because depending on your quasi-momentum, the coupling will actually have a slight frequency detunings with respect to the collective spin that we have. So this system actually becomes more complicated. But on the other hand, this brings in the capability of having S-wave interaction, because the atoms from one pancake to another, they are no longer indistinguishable fermions. So they can have S-wave interaction as well as P-wave interaction. And we can play games with balancing these interactions. So here's a new system that we actually supported the lattice inside the optical cavity to just make the pancake large and really smooth. The cavity is a great way, always smoothing things out. It's kind of funny thing, whether you like Rob working microwave or like myself working optics, we all love cavities. The cavity just defines modes really well, removes all the bandwidth that you don't want it to be in there. It just has a lot of good things. Anyway, it's a small joke. We made the lattice to be extremely shallow at this point. And now you look at this lattice, you will say from side to side, there's a gravitational potential energy difference. This is nothing but the mass of strontium atom times gravity times the lattice of lambda over 2. This is just simply telling you energy difference between individual pancakes. That's gravitational potential energy. This is not a gravitational redshift. And this is a lattice in condensed matter physics we call the von Neumann state. It's a lattice with a linear tilt. And the von Neumann states actually gives rise to, so we are now using lattice depths extremely shallow. And sorry for some of you who from outside of the field, I'm using photon recoil as a unit. But just to give you a sense, this lattice depth is about 10 times shallower than we would traditionally use in the lattice clock. 3 photon recoil is a feeble amount of energy to suspend atoms against gravity. And actually, by the time you go to 3 photon recoil, you can see the wave function of the von Neumann state really spread out. Those are the lattice site 0, +1, -1. So the wave function really spread over several lattice sites. And the first thing we never went there before, partly because we were not aware of this photon scattering problem until we really looked for very long coherence time. Partly because I was very worried at the beginning to use a very shallow lattice where the wave function is like spreading out. Maybe that would kill our coherence. But turns out that's not the case. And it was very, very satisfying to find out experimentally that you can drive the transition, for example, from on the same site, from site I, from ground state to the excited state, or because the lattice is so shallow, you cannot drive from site I to site I plus J. And this J could be like 20. You could actually create like weird coherence superposition where one atom is here in the ground state and it excited state, but it's living somewhere here. And it's living there in coherence superposition for how long? The coherence time can be as long as a minute almost. And so here shows like some initial energy measurement that we show. This is the carrier when I'm driving just I to within the same site G to E. But you can see the sidebands. The sidebands is nothing but the gravitational potential. I'm driving now from this site to that side by 4 sites difference, right? 3 site difference, and that would be this sideband here. Just 3 gravitational potential energy site away, and that happens to be 800 hertz each sideband. It tells you, by remember in undergraduate student when we were trying to ask you to measure G, you roll a ball and with a tilted plate, and the ball rolls down, and you can measure the G. And this is measuring G because it tells you mgh, how much energy there is. And you expand on one of those, the line width of that tells you the coherence. And if you expand this out, this is with 10 to the 5 atoms. And here's the coherence decay of the Ramsey fringe contrast. And that's like 36 seconds. Is actually part of that limited by the 120-second lifetime. And if you talk about just the coherence time, is actually 50-something seconds. So here's the trick we are playing. As I mentioned earlier, within each pancake, atoms are identical fermions, so they're interacting with a P wave. Now, because this lattice is so shallow, some of the atoms from neighboring sites can come in and interact with you. And that interaction is through S wave. The relative S wave, P wave, those are given by atomic properties. But the actual strength of the interaction can be, relative strength can be controlled by just controlling the site, the tunneling rate. So if you control the site, if you just vary how many photon recoil you use for your lattice, you can actually see the fractional frequency shift of your clock goes through 0. At this particular trapping depth of 12 recoil, suddenly the P wave, S wave just cancels out. And if you zoom that in, how well can you measure this? How good can you zero? Well, we can zero it at 10⁻21 level of the interaction. So for building clock at 10⁻20, that's good enough. But when you're trying to build a clock 10⁻22, this is something we'll come back to revisit. But that's being sort of the really exciting journey is you go through this, you learn a bit about quantum science, and you improve your measurement capabilities, and you go back to improve further of the atomic system. You would think you understand all the atomic systems already, but there's always tricks to play to control it, to make it better and better. I thought I put it in this slide just for our condensed matter colleagues. You can study dynamical phase transitions, and I maybe apologize, this could be a busy slide, but the whole point I want to make is, here's a CCD camera of the atomic distribution of this cigar-shaped lattice that's sitting in the vertical direction. And we can take an image of it, and every single pancake's density is represented by this profile on the CCD camera. Meanwhile, we can drive the transition off-site, so it's not S-wave dominated transition. And we can see how easy or how difficult to drive these transitions. So dynamical, you have a spin, and how easy can you make a spin to go from ground state to the excited state? Or once you drive up there, how long does it stay there up there? And there's apparently, there's a phase transition. From ferromagnetic, you just cannot drive it at all, to very easy to drive to magnetic. And what's beautiful of this is because we can take this one-dimensional image, we can actually plot this, as a vertical axis as an atom per site, just from this picture A, and then we can vary the detuning of the laser. Our laser is driving these spins, and it can immediately see this kind of phase transition diagram from ferromagnetic to paramagnetic in one shot. And this is just telling you like what we can plot this as excitation fraction as a function of the detuning. So you can take a cut through the number of atoms, whether it's 26 or 102, 182. You can see the line shape gets distorted from very hard to drive on the one side to very easy to drive on the other side. Or you can study this as a function of an atom per site with a fixed detuning, and you can cut it from this way, or you can cut it from vertically, and allow you to study these sort of a phase diagram of a dynamically driven magnetic plot. So coming back to the clock, as you can see, we always go back and forth and study a little bit of many-body physics, but then come back to the clock. You can compare now the upper half of the clock versus bottom half of the clock. And you can, this is so-called Allen deviation, which shows the fractional frequency uncertainty you can measure. This is comparing two clocks. If you think of upper half and bottom half of two independent clocks. And we can see actually this measurement precision goes all the way down to 10 to minus 21, 6 times 10 to minus 21. And we use this capability to measure gravitational shift across the entire crowd. For 1 millimeter, for example, we measure the slope of minus ones just by definition, that meaning pointing down, the clock slows down at 10 to minus 219. And it exactly, of course, agrees with the Einstein's prediction of general relativity, or at least for the first time we're measuring it at a few hundred micron, sort of a level of precision. The previous measurement that was actually done by my colleague Dave Wineland, he was able to use a single trapped ion, and I remember that experiment in 2010. He had two trapped ions, and they're sitting on two different optical tables, and they used a lab jack to move the optical table up by 33 centimeters, and they can see the time dilation difference. So this represents almost 100 times improvement on the measurement precision, because we are talking about 300 micron, 200 micron stuff. This is an artistic rendition of like, now you can talk about pancake by pancake, and the time is different. But what is to come, really? I think what's really exciting is, I think quite a bit, can we learn from people like Vladan Vuletic doing spin squeezing experiments, or Mark Kasevich, who used to be here when he first was thinking about spin squeezing. Can we learn from them and to entangle these atoms to further enhance the quantum metrology? And for that, we actually have experiment running where we have this lattice. This lattice can also be moved, can be used as an elevator. You can put atoms into these individual pancakes, and it just control the phase between the two running waves, and the lattice just moves up or moves down as well at will, without changing the quantum states. So we put a cavity around it. This is a cavity QED system. We can actually put it, once atoms are inside the cavity, we can actually do spin squeezing operation, entanglement operation. And you can move them out and move the next sample in and spin squeeze them. If I had not made a mistake of left my computer in by Steve's office, if I had my computer, I was going to put in a slide that my graduate student prepared from last week's data that actually showed the spin squeezing of 6 dB in the real experiment. And actually, for the first time, we are showing spin squeezing over macroscopic scales of 200 milliseconds. Like you can actually run Ramsey fringe with it, not just the 1 millisecond. So it's actually quite exciting. Like the fringe, we call the metrological Dave Wineland criterion, meaning whenever you do spin operation, entanglement operation, you lose some coherence, you lose some contrast in a Ramsey, and you want your spin gain, your entanglement gain outruns the loss of the contrast. So you have a real gain. And so that's something, actually, Actually, it's here. This is the data. I knew I prepared. I just didn't have a chance to cut paste into the PowerPoint slide. But this, you can see, this is actual spin squeezing. This is the actual loss of contrast because of spin squeezing. And this is the net gain. We are very, very excited, even though it's a feeble 3 dB, 4 dB, to actually show this is possible to push the clock better because of entanglement. So, remember I also talked about this crazy kind of ways to entangle atoms, not entangle coherently superposed atoms from over large distance in the vertical direction. So putting all this together, you can't help but start to think about, well, not only time is soft, as this picture, this artist shows, Salvador, but is it possible we can think in the near future, the next decade or so, where we can unite atom interferometer, that we are using the external degrees of freedom, and the clock, which is the internal degrees of freedom. If you had your will, of course, you can control all of them, right? Just as I was showing you, you can have a coherent superposition ground and excited state. You have the different locations. You can really start to do clock interferometers where gravitational, the GR, general relativity, entangles the clock with its spatial degrees of freedom via time dilation. And I think it's starting to feel like it's feasible, especially if we can push the clock precision just by another factor of 10 or 100, where you can start to be sensitive to time dilation of a few micron scale. And I can create these entanglement and so on in that time scale. And so we have been recently talking with Peter Zoller, Anna Maria Ray, and start to think about, this is a very weak gravitational field. Of course, it's a linearized gravitational field. How do you actually understand the GR effect with the spin model of the interacting effect? And what was really revealing to me was all the GR effect can actually be interpreted as you have atom in the ground state, photon comes in, driving into the excited state. The mass of ground state and excited state is different by h nu over c squared. Einstein's famous equation equals to mc squared. And so the ground state and excited state, you create a superposition, but they are sitting at a different mass and a different gravitational potential. And that's going to cause some dephasing, decoherence effects. Can we measure it? At 10⁻21, 10⁻22, yes. And so it would be really interesting to get to that regime. Now you can start to dream about, well, if I have 10 atoms, I entangle them in this direction. I have 10 atoms, I entangle them along this direction. The dynamic evolution will start to be different. And I don't know if this is a very fundamental, it's not a quantum gravity, nevertheless, be able to get to that level of measurement precision will be fantastic. And I would going to end here to just say, I'm really resonating with the Yale vision of building instrumentation. In some sense, building clock is nothing but it's building a telescope, allow you to see gravitational waves, search for dark matter by networking them together. It's also at the same time, you're building a microscope, because if you look down on Earth, you will be able to see how groundwater is moving, because time is not connected in this very sensitive way to the gravitational potential distributions. And you can use this to monitor our Mother Earth better. So I'm going to end on this point. Thank you very much.
So, we're about time. I'd love to welcome questions. People who feel that they need to head out, please go ahead and do so. But let's definitely take questions for Jun. And for the folks on Zoom who I think can't hear, I'm going to pass you the microphone.
Really amazing results. Thank you very much for a great talk. I have a really dumb question, so I'm sorry for the anxiety, but the thing that I was kind of curious about is if you're using entanglement like Newton space as a resource for metrology for the entangled atoms coming in, do you have any idea of what fidelity you would need with the entanglement in order to get a metrological advantage? And the second thing I wanted to ask is that entanglement is sort of like dual, from old results by Wiseman and all, to additivity. are there any ways that you could imagine conceivably practically changing the entanglement resource for adaptive experiments with something more like a multi-pass interferometer?
Okay. So Jack, do I need to repeat the question, or I think because
Carson is saying yes, and so if Carson says yes, then the answer is yes.
the first question, I think if I understand correctly, is whether there's a certain fidelities of entanglement that would be useful for metrology. I think, well, for metrology, depending on what metrology you're doing, certainly for the stuff that I talked about, clock, it's not a gate operation. It's not a, I'm not making a GHZ. You can certainly do that. That would be amazing to have. Maybe that will eventually get you 100 dB gain. Right now we are just talking about SpinSqueezing, and so rather than fidelity, what we really care about is as I entangle this, that I can reduce the quantum noise. But as I do that, that's cost, because whatever I'm doing, I'm still performing measurements or operations on those atoms, and they may lose some of the coherence. So there is some connection there, right? If you're doing gate operations, maybe the gate operation will have a back action on the activity. For me, the criterion right now is the reduction of the quantum noise should outpace the reduction of the contrast. Otherwise, you have done nothing useful. Your second question, which is whether there's different ways of entanglement. No. Can you repeat that?
So you can avoid entanglement altogether and reach the Heisenberg limit by doing adaptive experiments.
Okay.
And so I was just kind of wondering if that would make sense here, or are the timescale so short that adaptivity can be impractical?
Okay, so yeah, so the second question is you avoid entanglement altogether by doing some adaptive measurement gets to the Heisenberg limit. Actually, maybe you can talk further after this. I actually don't know how to do it. It would be great to learn from you the particular protocol and so on. You're maybe referring to some like a weak measurement that some people, no, that's not what you're thinking. There's something that you're thinking about, but we'll love to talk about what we are thinking about entanglement. In fact, very broadly, there are now new ways of thinking about quantum information processing, such as optimization. This is something we are definitely thinking about, like how do you entangle, and for certain goals, how do you increase both the bandwidth of your entanglement as well as the sensitivity. And those are the things we do think about.
Sure, let's take one more question.
Hey, thanks. So I believe you said something like a difference in rest mass will induce some gravitational coherence. Could you explain that better? I didn't understand.
Yeah, so this is basically the idea that where does the redshift time dilation come from? There's one way to understand this is actually, and this is a kind of an interesting way to think about. People remember in the atom interferometer when they were making coherent superposition of hyperfine states, and they throw atoms, one stays here, the other one gets a photon recoil, gets trapped, gets moved up there, and they can re-interfere. And there was some attempt to think about this is also testing the redshift, but turns out that's not. You're just really looking at the action of the gravity, right? The interferometer fringe. But on the other hand, if you can actually drive the optical transitions, where the ground state and excited state actually have different rest mass, then the picture is actually different. The atom which is moving up versus atom which is not moving up, they have different proper time. And there, when you re-interfere, you can actually lose contrast because they have gone through different proper time. So that's the connection to sort of a general relativity or time dilations into atom interferometer.
Okay, and you don't think about that as a coherent effect? You think about that as a loss of coherence?
Well, it depends on it's in that two atom picture. I think it's a dephasing. Not redshift is fundamentally just dephasing. You pick different trajectories. You come back. You can say the fringe gets washed away, but if you waited long enough, it will revive, right? Because it's fundamentally just a beating between the two phases. However, if you have more than two particles, or if those particles have a wave function that's extended, now that's question that's whether you call it dephasing or decoherence start to become something you can measure.
Okay, well, with that, let's thank Jun again for that excellent talk.
I think your microphones.